Okay, thank you very much. All are welcome. This is the
Thank
fifth
you.
show of our series. The Today's lecture is going to talk about congruences. So I will start from the definition of congruence. Last time we discussed equivalence relation on a set. The set considered there was not having any structure on it. But today we are going to look at congruence relation, equivalence relation on a set which is a semigroup. So if you have a semigroup, uh, a relation on a semigroup. So in the last discussion, we were looking at a set X, just a plain set. It doesn't have any structure on it. But right now, we are having the structure of a semigroup. So we will look at the interaction between the binary operation of the semigroup and the uh, uh, binary relation rho. So a binary relation on a semigroup is called left compatible if whenever S is related to T, then AS is related to AT. So if it so happen like this, we say the relation is left compatible. And the relation is called right compatible if for any element A of the semigroup, if S is related to T under rho, then SA is equal to is related to TA under rho. It's supposed to be rho actually, not R. It's a typing mistake there. And then we say the relation is compatible if whenever S is related to T and X is related to Y under the relation, and the product XT is related to TY. So these are the defining properties of a relation that are called left compatibility, right compatibility, and compatibility of the relation. I believe these properties are clear from their definition, even from the name. A relation is left compatible if on multiplying elements uh, that are related from the left by a common factor, they still remain to be related. And on multiplying a common factor from the right, the relations are still, the elements are still related. And then we say compatible if the product of any two related is still uh, related. And then so a left compatible equivalence relation. So a relation that is left compatible will be called a left congruence. And if a right compatible relation is an equivalence relation, then we call it a right congruence. Then a congruence is a compatible relation, which is an equivalence relation. So that is the definition of a congruence. So a congruence on a semigroup is actually an equivalence relation which is compatible. And then we have a lemma here characterizing the congruence on a semigroup. So in a semigroup, a congruence, a relation is a congruence if and only if it is both left and right congruence. So you see, when we define left congruence and right congruence, actually the definition, if you look at the two definitions, they are not the same. Saying that a relation is left compatible and right compatible does not mean it should be compatible. So, but for a congruence, if it is both left and right congruence, then that relation must be a congruence. So the two are equivalent. Where you either say it is a congruence or you say it's both left and right congruence. But for compatibility relation, it's not necessarily that if it is left congruence and left compatible and right compatible, then it must be compatible. So the essence of having a congruence relation on a semigroup is actually to partition the semigroup into the equivalent classes. Remember, we talk about this set. If you have a congruence on a semigroup S, then that congruence, by the definition, is an equivalence relation. So it will partition the semigroup into equivalent classes. And then the set of equivalent classes is the one we denote by S by rho. So this is a quotient set of S by rho. And if rho is an equivalence, is a congruence, then we can define a binary relation on this quotient set in a natural way by multiplying two equivalent classes. So the equivalent class of A under rho is multiplied by the equivalent class of B under rho to produce the equivalent class generated by the product of A and B. So there is a product already of A and B in the underlying semigroup. So one will multiply equivalent classes in this way in order to make the quotient set into a semigroup. And this will not be possible unless if the equivalence relation is a congruence. So actually this binary relation, this relation we have defined, this binary operation here that we have defined endured S by rho, the quotient set with a semigroup structure. And so the multiplication, because we define the multiplication in term of equivalent classes, and whenever you do that, it is a normal thing to check whether the multiplication is actually well defined. Because if one is taking two equivalent classes, equivalent classes are referred to the generating element or the representative of the equivalent class. So if you take A and A prime from the same equivalent class and you refer to that equivalent class as A row and also refer to it as A prime row, you would want to know whether the product, even by changing the name of the equivalent class, the product will still be the same. So only then the operation will be well defined. So when we define on this quotient set binary relation by multiplying equivalent classes, the multiplication is referring to the generating element or representative of the equivalent class. So in that sense, we have to check to see that if we change the choice of the representative, if you pick A prime here and B prime, where A prime and B prime are coming from that same equivalent classes, will the product still be the same? Because if the product is not the same, then we are not having a binary operation, and so we have to check that. So this is what we checked here, that if A row is equal to A prime row and B row is equal to B prime row, so meaning we have the same equivalent class but with a different choice of class representative, then we want to see that the product should also be the same. But the meaning of this is that A is related to A prime and B is also related to B prime all under row. And because row is a compatible binary relation, so the product AB will be related to A prime B prime. This is by compatibility. So if the relation is not compatible, this arrow will not be able to actually, this implication will not be valid unless if the binary relation is compatible. So it is the compatibility that allow us to get from this point down to this point. And once we have this is exactly stating that the equivalent class generated by AB is the same thing as the equivalent class generated by A prime, B prime. And so therefore, this is demonstrating that the binary operation defined on
It's
the
well defined.
quotient set is well defined, yes. So so therefore, we have a semi-group because it will now be a routine checking that this binary operation is associative because associativity. Since if you look at it, the operation is actually in term of element of S, and already associativity happened with element of S being a semi-group already. So therefore, associativity is an inherent property which this operation will inherit from the same associativity from S. And so therefore, what we have here is a semi-group which we call the quotient semi-group of S by rho. So rho here is a congruence. So which means unlike in group theory, if you want to form a quotient group, you require a subgroup. But here, what you require is a binary relation, which is a congruence. So we form a quotient semigroup by using a congruence rather than using a sub-semigroup. So we don't use a sub-semigroup, but we will see the link actually in the last part of this discussion. We try to demonstrate the link between the group idea of forming a quotient group using a subgroup, and this idea of forming a quotient semigroup using a congruence. And so once we have a quotient semigroup, then we can think of stating something like the first isomorphism theorem. So this is the first isomorphism theorem of semigroup theory. You have two semigroups and a morphism. This is a semigroup homomorphism. If you have a morphism from S to another semigroup T, then the relation kernel of phi, this morphism, you remember we say kernel of phi, which is phi composition, phi inverse, is an equivalence relation. So if phi is a morphism between two semigroup, then kernel of phi will always be a congruence on the domain, on the semigroup S, which is the domain over here. So we have a congruence, which means I can use kernel of phi to form a quotient of S. And so therefore there is a monomorphism psi from S by kernel. So this quotient semigroup exists because kernel is a congruence. Into T, this is a monomorphism onto T, so monomorphism, which means S by kernel of phi will be isomorphic to T, such that the image of this monomorphism is equal to the image of phi, and that the diagram here commutes. So I have a semigroup homomorphism, and naturally from the semigroup homomorphism we have a morphism. This is the natural morphism because we have this kernel, kernel of pi, we use it to form a quotient semigroup, and then there is the natural homomorphism where every element of the semigroup is mapped to the equivalent class where it belongs. And then the theorem is that this monomorphism exists such that S by the kernel is isomorphic to the image of phi in T over here. So which means there is the isomorphic copy of the quotient semigroup by the kernel into T. So that is what it means by this diagram commutativity of the diagram. This is a categorical language. It's just to say that if I compose this mapping kernel natural, the natural homomorphism with this psi, the result should be equal to phi. That is what it means. And then the proof is actually similar to what we have learned in group theory. To show this is a congruence, first we show that this thing is a congruence. To do that, you take two elements of the kernel. And if A and A prime are element of the kernel, it means they have the same image under phi. Likewise, B and B prime are having the same image under phi. And so therefore, since phi is a morphism, one can see that the image of the product of the images, this is by morphism property of phi. And then because of the assumption that we have as to the fact that A phi is equal to A prime phi, then we can replace A here by A prime and B by B prime. And then we again apply the morphism property of phi to have this. And so therefore, kernel phi is a congruence. Because if you have any two related, A is related to A prime and B is related to B prime, the product AB will be related to the product A prime, B prime. And that is what we define to be compatible relation, compatibility of the relation. So the kernel is compatible, and we know we have proved in the last discussion that the kernel of phi is an equivalence relation, so we have a congruence on the semigroup. And then if we let rho to be the kernel, so this is just for the sake of simplicity of the notation. So instead of we'll continue to work with kernel of phi, this is too clumsy, we use rho. So we write kernel of phi to be rho, and then we can define on the quotient semigroup this psi by, if you take any equivalence class of A under rho is the kernel now, it will be mapped by psi to the image of the generator under phi. So if you look at this diagram, it has revealed everything because element here are kernel equivalent classes. So if you take a class, you map it to the image of the generating element or the class representative inside here, the image under phi. And that is what we did even in group theory. And once you do that, you can easily check that this psi as defined in this way is both well defined and 1 1. So it is well defined and 1 1, 1 to 1 because of this arrow like this, and well definedness if you come back. So if you go like this, you have well definedness, and if you come back, you have the 1 1ness. So this is showing that the mapping is well defined and it is 1 to 1. And it is also a morphism in the sense that it preserves composition of kernel classes. If you take the image of a product of classes of row equivalent classes under psi, by the definition of the product we have defined in the quotient semigroup, this is AB row. And then AB row will be mapped to AB phi by psi. And phi is a morphism, so it preserves the composition. So over here, you can pass phi over the product. So you have A phi and then B phi. But then this is what we call the image of the row equivalent class of A on the side. And that is the image of the row equivalent class of B on the side as well. So therefore, this side is composition preserving, and so therefore it is a morphism. And then clearly, by the virtue of the definition of the way we define psi, we see that the image of psi is equal to the image of phi. And the fact, the commutativity of the diagram that we said here is to see that if you compose this natural homomorphism with psi, you recover phi. And that is what we have demonstrated here. Actually, by the virtue of its definition, psi satisfies the property that for all A in S, A row natural under psi is equal to A phi. And that means row natural composed with psi will give you phi, because this is happening for all A in S. And so therefore, the first isomorphism theorem of semigroup is established. And we can generalize this theorem because if you come back here and look at the theorem, it is talking about kernel. So if you take any equivalence relation that is contained in the kernel, the theorem is also true. So you don't have to work with the kernel in its entirety. You can just concentrate on a subset of the kernel and the theorem will still hold. So if I take any row, a congruence on S that is contained inside this kernel of phi, if you have this homomorphism and you take any congruence contained in the kernel of the homomorphism, this diagram is still valid. So this is what the next theorem 4 here is saying. If you have a congruence on a semigroup and a morphism between a semigroup S and some other semigroup T, such that the congruence is contained in the kernel of that morphism, then there is a unique morphism. So one can describe a unique morphism from the quotient semigroup S by rho into T, such that the image of that morphism is equal to the image of the originally given morphism phi, and that the following diagram is commutative. This diagram is commutative. So in the sense that if I compose rho natural with psi, that should be equal to phi. So, and the existence of this psi is unique. So there exists a unique morphism. So in fact, that is the added advantage that we have gotten here. There exists a unique morphism into T here. And then the diagram is commutative. I believe the proof is again routine, and it almost require no extra explanation because it's almost what we have just discussed in the last theorem 4. If you define that psi by, this is just how we define it even the other time. The only difference between this proof and the last proof is the fact that rho here was the entirety of the kernel, but here rho is assumed to be contained in the kernel. And once you have that, you can can check that if you define psi again by mapping every row equivalent class to the image of its generator under phi, that psi is well defined uh, by this loop. It is well defined here. You can see that if I take two row equivalent classes, but referring to different class representatives, this means A is related to B under row, and that is implying that A will A comma B will be in the kernel. This is because we assume row is a subset of the kernel. So that assumption is what allows us, the fact that row is a subset of the kernels, it was allow us to get from this level here to this level over here. And once A and B are related under the kernel of phi, it means they have the same image under phi. And then, so therefore, psi here is well defined. The theorem here didn't say it is a monomorphism, but it's just a morphism. So well-definedness is all that we require. But in the last theorem, we were looking at a monomorphism, and so therefore we had to go back. The arrows must to also go back. You must also assume images are the same and prove that the pre-images are also the same. The fact that it is a morphism is routine, is almost the same thing, and by the virtue of the definition, again, you can see that the image of psi is equal to the image of pi, and commutativity of the diagram is also following here. And then the uniqueness is again clear, since if you are to have any other mapping from here to T that will make this diagram to commute, that mapping must be defined by sending a point here to the image of their generators under phi. And so therefore, it must be the same thing as psi. So if you assume any other map from here to there satisfying the fact that the diagram here commute, that mapping must be equal to psi. So therefore, uniqueness is also clear from the definition of psi. And so we have this theorem. This theorem will be useful in many occasions in the theory as we move down into the theory. And then we have the analog of the third isomorphism theorem also. If you have two congruences on a semigroup S, such that one is contained in the other, then this thing here, this is a subset. This is just like a relation, uh, a relation on the quotient semigroup, because S by rho is a quotient semigroup since rho is a congruence. So this is a relation on the quotient semigroup defined in this way. So it is actually the X2 equivalent classes under rho are related. X rho is related to Y rho if and only if X comma rho, that is the generators, are related under sigma. So if it so happen like this, you form this set of ordered pairs, which is now a binary relation on the quotient semigroup by rho. This is a congruence. So the first claim of the theorem is that this is a congruence. And then if it is a congruence, then you can talk about doing the quotient of the quotient by that congruence. So S by rho by sigma by rho. And the theorem is again claiming that this quotient of the quotient is isomorphic to S by sigma. So in other words, you don't achieve anything by taking quotient of the quotient. If you just take quotient semigroup and you quotient it again, you just get it's isomorphic to the quotient semigroup. So no more information one can achieve by taking quotient of the quotient. This is what the third isomorphism theorem is saying here. And this theorem is just application of the first isomorphism theorem and the theorem 4 that we generalization of the first isomorphism theorem. So by that theorem 4, because there is a unique morphism psi from S by rho into S by sigma. So in other words, if you, in that theorem, you replace T over here by S by sigma, then there is a unique morphism. This is what how you apply theorem 4 here. And so such that this diagram is commutative, because naturally you have a morphism. So your morphism phi in theorem 4, you regard it as sigma,
No, tẹ́ bá ti lọ
you regard it as sigma natural,
tẹ́ bá ti
the
lọ
natural homomorphism
tọ́jú
of sigma
ìtọ́jú
into there. And once there is a homomorphism, and this one is contained inside the kernel of this, because
ó wà
we know that sigma
tẹ́ bá
is
ti lọ
contained, rho is
ìtọ́jú
contained in sigma. There is some interference. Okay.
òun náà ni.
So we know that rho is contained in sigma, and so therefore we can apply theorem 4 to say that there exists a unique morphism from the quotient semigroup here into this semigroup. This is just replacing T in theorem 4. This is representing T in theorem 4. So once you have this, you can check what is the kernel of this margin. Since it's morphism, you can talk of the kernel of this psi. So kernel of psi will be the set of all ordered pairs having the same image under psi. And so that kernel, one check that it is given by this, because psi, rho A under psi is A sigma. And so therefore, if you say X rho psi is equal to Y rho psi, that should be X sigma equal to Y sigma. And that is the same thing as saying X comma Y belong to sigma. And so it is exactly what we were given in the theorem here. So kernel of this psi is equal to sigma by rho. And so if I now look at this sigma, this psi, this mapping here, psi, and I see it as I have a semigroup and a semigroup homomorphism into another semigroup, then I can talk of kernel of this mapping so that I have a third semigroup, which is S by rho by the quotient of S by rho by the kernel of this mapping. And if I have that, I can apply the first isomorphism theorem to see that this particular diagram commutes, because I have a homomorphism or morphism, and then so there will be the quotient semigroup of this one by the kernel of this map. And kernel of this morphism is sigma by rho. And so what we have here is a natural homomorphism sending every point here to the equivalent class it generates. And so this is the kernel. So if I apply the first isomorphism theorem, it says there is a monomorphism phi into T, and this is the T here. This is S by sigma, which is our T. So in other words, there is a monomorphism. But we know that this monomorphism will be onto because of the fact that this one is also onto. This is onto, and we know this monomorphism here is defined by sending every point here to the image of its class representative under psi, and psi is onto. So therefore, this monomorphism is an isomorphism. So this phi is an isomorphism. In other words, S by sigma, S by rho by sigma by rho is isomorphic to X by sigma, thereby proving the third isomorphism theorem. So actually, the thing to take note is here in semigroup theory, we use congruences in forming quotient semigroup, not sub-semigroup. Whereas in group theory, one will take a normal subgroup and then we form a quotient group using normal subgroup. Even though there is still connection between that construction via using the normal subgroup, because normal subgroup can be seen to be binary relations that are congruences actually, because those are the equivalent classes, the relation generated by congruence modulo relation. So in fact, that is actually the idea. So this is to look at the smallest congruence generated by a given binary relation, because it's not every binary relation in a semigroup that is a congruence. And from what we are seeing from the discussion, we can see that it is the congruences that are of interest, because those ones will be the ones used to construct new semigroup out of a given semigroup. So if you have a congruence, you can quotient the semigroup by the congruence, thereby creating a new semigroup out of a given semigroup. But if you are given just any relation, it is not necessary that the relation is a congruence. Even if it is not congruence, one can generate a congruence using that given relation. And this is what we are going to look at: the congruence generated by any given relation in a semigroup. And so for that, we say the intersection of a non-empty family of congruences on a semigroup is again a congruence. So this is a claim that can be easily checked. If you take a whole family of congruences, their intersection will still be a congruence, because this family is an equivalence relation. It's a family of equivalence relation. And so the intersection will still be reflexive, symmetric, and transitive. And so therefore, its intersection of all the entire family will be an equivalence relation. And then the fact that it is a congruence can be checked by just seeing that it is again a compatible relation on the semigroup. And so therefore, for any given relation R, we can talk of the unique smallest congruence containing R, and we denote it by R sharp. So this notation we use, R sharp. So by R sharp, we mean the smallest congruence on S containing R. And that should be the intersection of all congruences on S containing R, because intersection of sets will always be the smallest of all of them. So therefore, that is it. But you see, this definition is not a usable form of a definition. One cannot apply it. In application, it doesn't help. So we require a more practical characterization, one that can be used in application. So, and in fact, this is what we are going to see how we can characterize this R sharp. This is the smallest congruence on a semigroup containing a given relation R. And so for that, we just have to do this construction for a semigroup R on S. The relation RC is now defined to be the set of all XAY, comma XBY. So it's also a relation on the semigroup such that X and the Y are element of the semigroup with identity adjoint if necessary, and A, B are related under the given relation. So for any member, pick any pair in R, and then you sandwich the pair, with common elements of the semigroup with identity if necessary, and then you form RC. So you see this RC clearly from its definition, because X and Y are coming from S1. So there will be time when you choose X and Y both to be equal to 1, because there is always 1 inside the semigroup. So if I take X to be 1 and Y to be 1, XAY is just A, and XBY is also just B. So in other words, every member of R is also inside RC here. So this RC is claimed to be the smallest left and right compatible relation on S containing R. The fact that it contains R is clear from the definition. I've explained that. But then it is a left and right compatible relation. So it's a small such relation containing R. So to see that it is clear that it contains R, I have explained this. But then to show that it is a left compatible relation, one will take UV from RC and take any S and then see that take any omega or w in S, and see that if you multiply u by w from the left and v by w also from the left, the two remain to be related under RC. But then if uv are from RC, by the way we define RC, it means I can find x, y from the semigroup identity adjoint, and A, B are related, such that U is XAY and V is, uh, this should be XBY, not A. This is XBY, because that is how we define element of RC. And if that is the case, then it means UV is equal to UXAY, and this should be this is WU. The first one is WU, and then the second one should be WV. These are just typos, please. Uh, so this is WV. I'm talking about if I multiply this V by W from the left, it should be uh, WXBY, and this one should be WXAY. Now, if you look at the bracket, you have WX and Y. You sandwich A with WX and Y, and also you sandwich uh, B with WX and Y. You see, common, the same element, because this WX must also be in S1. And so therefore, what we are having here, this WU and WV are RC related, because any ordered pair of this type, this comma this, belong to RC. So if WU and WV can be written in that form, then they are RC related. In other words, if I take UV RC related and take any W and multiply this pair from the left by W, the result still is in RC. And so therefore RC is left compatible. Right compatibility is achieved in a similar way. And then to see that this RC is the smallest, because the claim of the theorem or lemma is that it is the smallest left and right compatible relation on S containing R. So we have seen that it is left and right compatible and it contains R. And what remains to be seen is that it is the smallest. Meaning if I have any other relation satisfying this requirement, that is left, right, compatible, and also containing R, then that relation should also contain RC. In other words, RC is the smallest. So this is what, so if you suppose some other relation is existing, S, and it's left, right, compatible, containing R, then it follows that for all xy in S1, the semigroup with identity adjoint if necessary, and then for all elements of the relation R, xay, xby will be in S. This pair is in S precisely because S is left and right compatible. If I take this pair and multiply by A from the left, the result should be inside S. And if I take the pair again and multiply by S, so and multiply by Y from the right, the result should be in S, because this pair is also in S, since S contain R. And so therefore it means all these pairs of this form are inside S, but all the pairs of this form are RC. This is what we define RC to be. So it means RC is inside S as required. So it means RC is the smallest left-right compatible relation containing R. So we have just characterized the smallest left and right compatible relation containing R. And this compatible relation containing R, which is the smallest, is having these further properties, that if R is contained in S, then RC will be contained in SC. And also if you find the C of the inverse is the inverse of the C, actually. And then this C the smallest left-right compatible relation containing a union will be the union of such relations. So therefore, it is union preserving. These properties are also immediate. One can easily check these properties. I'm not going to go into the proof here. And then we have another lemma. All these lemmas are in preparation to this characterization of R sharp. R sharp is the smallest congruence relation containing R. So we have one piece here which we present in a lemma, that if you have a relation R which is left-right compatible, then the composition of R any number of time is also left-right compatible. So if I have R left-right compatible, then R square will also be left-right compatible, R3, R4, R5, Rn, for all n. All this, if I compose as many times as possible, the, the, the composition will still remain to be left-right compatible. So this is also not difficult. It's just straightforward actually to prove this lemma here. And the proof is contained in the book. One can check. And then we now have a characterization of R sharp. And R sharp is the smallest congruence relation containing R. In other words, it's the congruence on S generated by the relation R. So if you have any relation whatsoever, there's no any condition attached to this relation. If you have any relation on the semigroup S, and then you define the smallest congruence relation containing R is, is, is equal to the equivalence generated by RC. If you remember from the last lecture, we did actually characterize this equivalence. We say it is the transitive closure of RC union RC inverse union the identity to the power of infinity. This is our notation for transitive closure, and this transitive closure is the union over all n of the compositions, the composition of all these relations. We have defined it actually. So I think there is no need going into the detail of the proof because most of the content are self-explanatory. I think by revealing this, we have exposed what the proof should be. So I think this is the characterization now for that particular congruence. So if you have any relation and you are looking for the congruence generated by that relation, this is the way to generate it. And this is the proof actually. So to state that, because this characterization over here is a little bit, uh, what do we say? Maybe we say this is not interest. This is from the outside actually. If you want to go inside and see what is going on, if you want to do an intrinsic type of characterization, so that to see what is going on inside, so you can have a corollary to this, but before the corollary, we just present a small terminology here. So if you have element C and D in a semigroup such that C is XAY and D is XBY for some XY in S, and some where A and B, the A and B here, that C is the sandwich of A with X and Y, and D is the sandwich of B with X and Y, where the A and B are elements that are either R related or R inverse related. So such elements C and D are said to be connected. We say C is connected to D by an elementary R transition. It happened in this way. So if you remember in the last lecture, we did present something like this when we characterize the equivalence generated by a relation. So this is the characterization. In fact, it is just stating this theorem in another way from the inside. So what we are saying, given any relation, two elements are related under R sharp if and only if they are either equal or there is a sequence of elementary R transitions that get you from A to B. So, and I think this is a more practical, usable characterization, because this is mostly how one would use the characterization. If you want to establish that A is related to B under the smallest congruence generated by R, you either show that A is equal to B, or you produce a sequence of elements Z1, Z2 up to Zn, uh, that get you from A to B by an elementary R transitions. So this is actually uh, another way to view that characterization of R sharp. And then just to finish up, we because R sharp, we say is the smallest equivalence relation contained in R. Then one can also think of what of the largest congruence contained in R, because we are now R sharp is the smallest contained in R. So R is inside R sharp, but it is the smallest, something like the like a cover. It is like a cover of R. But then think of having a core. What of the biggest equivalence, biggest congruence that is sitting inside R? And this is what we denote by E flat. So if E is an equivalence, so for that, actually we define that concept on an equivalence relation, not any general relation. Because here you see, when we are talking about R sharp, we take any arbitrary relation. But if you want to define the largest congruent contained inside a relation, you have to resort to limit yourself to equivalences. So I can talk of the largest congruence sitting inside an equivalence E. So for an equivalence E on a semigroup, we define uh, this E flat to be the set of all ordered pairs A comma B, such that there exists X, Y in the semigroup with identity adjoint if necessary. This means X and Y can be equal to 1, even if there is no one in the semigroup. And, and then such that XAY, XBY are E related. So for any such AB satisfying this, we put A comma B to be in this set. So therefore, this is again a relation on S. So it is this relation that we characterize to be the largest congruence sitting inside E. And this is the content of theorem 11 here. We say for any equivalence relation on a semigroup S, E flat is the largest congruence on S contained in E. And that is it. I think so. So that is it. Actually, we have characterized the smallest equivalence relation containing a relation, and also we talk about the largest equivalence relation contained inside an equivalence. And so here is just to go back to the discussion on equivalences. Um, you can do this discussion from this point to the end, maybe on a set. It doesn't have to be a semigroup. So if you remember in the class of all equivalence relation, there is the order relation of containment. And then with respect to the partial order of containment subset of, if you take the class of all equivalences, then some equivalents are subset of some other equivalents. So you can see the order relation, and you can talk of the upper bound, least upper bound, greatest lower bound, and so on and so forth. So in that class of all equivalence relation, it is a partially ordered set. The mix, which is the greatest lower bound, and the join, which is the least upper bound of any two equivalences, rho and sigma, are given by this is the meet, it is the intersection. Because the meet is the smallest equivalence contained inside rho and sigma. And that should be the intersection actually of the two. But then the join is the smallest equivalence containing rho and sigma. And this one is characterized by the equivalence generated by their union, because the union of two equivalents may not necessarily be an equivalence relation, but then you can generate an equivalence relation using it, and that equivalence relation generated by the union will be the smallest equivalence relation containing the union, and so the smallest containing both rho and sigma. And from one of the theorem we discussed in the last lecture, this is characterized uh, by taking the transitive closure of this relation over here. And then we utilize some of the characterization we have discussed earlier to come up with this characterization of the join. So the join, in other words, the smallest equivalence relation containing both rho and sigma is characterized by the transitive closure of their composition. So that is it. And then this is just to say what is happening, because uh, if you say it is the transitive closure of the composition, you are just saying that A is related to B under the join if and only if for all natural numbers n greater or equal to 1, there exists element x1 up to x2n minus 1 in the semigroup, such that A is related to x1 under rho and x1 is related to x2 under sigma, because you are composing. You are saying this thing is sigma composition, rho composition sigma, union rho composition sigma square, union rho composition sigma cube, and so on and so forth. And so you can see this transition is, is, is self-explanatory, which means I can get from A to B by a sequence of this type. And so this is actually the characterization. But then the most important corollary here is in this is the special situation where rho and sigma commute. So if it happens that you have equivalence relations to rho and sigma and they are commutative, meaning the composition of rho with sigma is the same thing as composition of sigma with rho, then the meet, the join is nothing but the composition. So you don't need to take the transitive closure. Just compose the two and that is the join. There is no need to take in the transitive closure. And this is very serious here actually, because this transitive closure is an infinite union. So just commutativity is making an infinite union to be just one single term of the union. I think that is very serious over here. So this is just to close this discussion. I have one last uh, concept that I think I should talk about, the concept of risk congruences. And this is the one that will reveal the connection between the ideals and the congruences, because there is naturally a congruence one can define out of an ideal. So if you have any proper ideal of a semi-group, you can define using that ideal a congruence on the semi-group. And this is how you define the congruence. Just take the Cartesian product of element of the ideal, union the identity. In other words, two elements are related under rho I if and only if they belong to the ideal. So all elements of the ideals are related to each other, and then members that are not in the ideal, they are related to only themselves. They form they relate only them to themselves. So if X is not in the ideal, X is related to only X and no any other element. But every other element of the ideal is related to every other uh, element of the ideal. So therefore, you define this relation in this way, and then you see that it is a congruence on S. It's not difficult to see, because is an equivalence relation, and it will be a congruence because of the fact that you are dealing with an ideal. Dealing with an ideal guarantee that if you take any pair and you multiply with a common factor, the ideal will absorb the product, and so therefore the pair will still be related, and then so it will be left and right compatible because we are dealing with an ideal. So such a congruence is the one we call Rees congruence. So any congruence that is defined in this way uh, via an ideal, that two elements are related if they belong to the ideal, and other members not in the ideal are just singleton related to only themselves, is called a Rees congruence. And then from what we have discussed, if you have a congruence, you can form a quotient semigroup using the congruence. But then we have just described what the congruence is. All elements of the ideal are related to each other. So one class of the congruence, one equivalent class is the ideal I. Union members not in the ideal will form singleton classes. So union the singletons of the members not in the ideal. So this will be the semigroup, the quotient semigroup. And this semigroup is uh, actually, this is the nature of the element, but it is convenient to write this quotient semigroup as SI. Most of the time, we drop row, we just say SI. We call, instead of referring to the congruence, we refer to the ideal. So because the congruence is generated by the ideal, and so therefore we just say Si. And I here, one should see it as a congruence, not uh, a subset of S. And think of the element of I, the element of the semigroup as I together with element of the complement of I, because that is what the elements are. It is I is one element of the quotient semigroup, and then the remaining element of the complement of I, they form one singleton classes. And so therefore, that is how we think of it. And because I, in that semigroup, when you do the multiplication, the composition, if you take this class and multiply by any other uh, element, this is an ideal, it absorbs the element of S, so you always get the ideal. So if you multiply I with any other class, you get I. And if you multiply I with I, you get I. So I is just like behaving like the zero element of the semigroup. And so we simply, instead of writing I, we just write zero, because I is the zero of that semigroup. And then we write the remaining members of the semigroup without the bracket, the set bracket, because we just write them as X in S that are not in the ideal. So this is how we think of that semigroup, and where all product falling that are not in here are zero, because it is possible to take element here and multiply them X and Y, and the result is not inside uh, S. It is not in I. If the result is not in I, then we declare it to be zero. This is how we think of this semigroup actually, and we call the semigroup as the Rees quotient semigroup of S by I. I think I just give an example here to demonstrate this concept of the Rees quotient semigroup. If you take the semigroup of natural numbers with respect to multiplication, the set of all even natural numbers is an ideal. And then n by I, the Rees quotient semigroup, is this one. So what we do here is this whole I, all the integers, you group them together and call them zero. And then the complement, which is the all the even integers, you call them zero, and then the complement, which is the odd integers, you write them as 111. And so that is what we mean by the Rees quotient semigroup. So this is the Rees quotient semigroup of the semigroup of natural numbers uh, by the ideal of even natural numbers. So you see here, if you multiply Any product is inside here, and if you take any number, uh, because we have already called this zero, so if this is already a semi-group now, and it is a semi-group with zero. Zero is, this zero is not zero, so to say, it is the entire ideal that we refer to as zero. So this is the entire semi-group of, this is the entire subset of the even integers. We call it zero because it acts as zero. And so this is what is called the risk. This is a connection between the ideal of a semigroup and the congruences. So actually in forming a quotient semigroup, we use congruence. But then when one is talking about Rees quotient semigroup, one should understand that it is not the ideal that quotient the semigroup, but the congruence generated by the ideal. And so I think that point should be clear. Otherwise, there will be a lot of confusion in the clear understanding of the concept in the theory later on. I think this is my last slide. Thank you very much for your time.
Ah, thank you, Dr. A.T. Imam, for taking us through today. We appreciate your effort because this sixth really should be the sixth lecture, but actually the fifth lecture because we were unable to have our lecture for the fourth lecture last 2 weeks as we were distracted by the national national calamity of electricity. But we thank God that the fourth lecture were able to, I think, came up. We repeated it last week or so. We thank you for all what you have been doing. We thank you for your credit. We thank you for your data. We thank you for your time. Thank you for the energy you have used in compiling all these things. It is not easy, as you must have taken your time to study this